Okay, and so that lab report, the calculations are going to be snarly. All right, you've already seen, right? We did them in class. If that all made sense, you're like, yeah, I can knock those out. Great, but I recommend you try them before Friday. And actually, it would be if you haven't tried them already and don't want to come this afternoon to talk about them, I recommend you try them before Wednesday so that you can come in that afternoon and get help. Also, I'll be available. We can talk about it on Thursday evening as well. Um, Questions on what we're doing, where we are? Nope. Okay. So last time we talked about the Michaelis-Menten constant, not constant, but the Michaelis-Menten equation. Um, so just to remind you, we have the initial rate of reaction is equal to the max rate of reaction, and that maximum rate will change for how much enzyme you add. Remember that for this, the cool thing about this equation is it doesn't matter how much enzyme you use. Enzyme does not appear in that equation at all. So we have whatever substrate we're using, what its concentration is. We have whatever the max rate is that we can determine if we've done a few substrate concentrations, and then we have the initial rate here that's going to come out of that. The assumption, one of the assumptions, we're going to do the derivation today, and I want to show you the assumption, but one assumption is that the concentration of total enzyme that's been added to the reaction is much, much smaller than the concentration of substrate. All right, so you've got an enzyme, it should be turning over a lot of substrate. You don't want to have enzyme be kind of equal to substrate. Questions so far? All right, then I want to remind you really quick about kinetics. This is kinetics, this is Michaelis-Menten kinetics. And I want to remind you that we do these sorts of things. So if I have some reaction where A is going to B, I can have some rate constant related to that, K1. And the way I would talk about the rate for that is the rate would be equal to, and you might see the rate expressed in calculus speak, the formation of A. D is a little bit, the change in A over the change in time. Okay, so sometimes you'll see rate expressed like that. We won't do anything with the calculus, but don't be thrown by that. What's this rate equal to based on what I've given you here? Assume nothing funky is going on there. That's kind of the reaction. There's, it is not B over A. B does not affect how fast this reaction goes. B affects how fast this reaction goes. I haven't drawn that arrow, right? But it would make your reverse affect how fast your reverse reaction goes.
Isn't it the rate law is like K times the concentration of A?
Yeah, so it'd be K1 times the concentration of A would determine how fast that rate goes. Does that make sense? Is that ringing bells? Do you remember that? Yes.
Wouldn't it be negative because it's consumed?
It's the rate of it. You're right. That should be the formation of B. So you mean right here. I agree with you. The formation of B, right? The way I had it was the disappearance of A, and it should have been negative. Questions? Questions on what Daniel just brought up? Okay. So that's our basic format here. Rate constant time the concentrations of things of the reactants going in. And that'll be important here. So what we're going to do is we're going to think about a model for how enzymes react. And this is a super simple model. We have an enzyme and we have a substrate. And we say that the enzyme and that substrate is in equilibrium with an enzyme-substrate complex. All right, and that equilibrium has a forward rate that we'll call K1, and it has a reverse rate that we will call K minus 1. All right, no, these little numbers here don't matter, but I'm following conventions that are in all the textbooks for this. And then we have a rate that the enzyme can, once the enzyme has the substrate bound, we have a rate at which it can turn that into product and then release the product. Very simple enzyme model, but this works for so many things. Okay, it's a really, really good system. My previous research where I was actually working on enzyme kinetics has worked just fine. P, product. P is product. Okay. So if we think of, so this is what our model is, really very, like I said, very simple. And part of why we're going through the math today, I'm going to expect you to understand certain things about that, like where we have assumptions. Okay. I expect you to understand assumptions. I expect you to kind of have a good feel for this. I'm not going to ask you to derive it, but what I'm going to do is I'm going to test your understanding using what I call graphy things. And I'll show you some graphy things at the end here. All right. But if we have this model, then what we can do is we can say that the rate of product formation, or the rate of reaction is equal to, you know, the change in product over change in time, right? And how would I express that? Oh, forgot one thing you'll need. That's a hint. How would I express the rate of product formation given this?
It 3 times the concentration of E times S.
Yep. Not E times S. ES is one thing. It's enzyme bound to substrate. Okay? So this, right? Very simple. All right? What's the problem with this? Enzyme substrate complex is very hard to measure. All right? How are you going to measure how much enzyme is bound to your substrate? All right, and there are fancy techniques where some people would be able to do that, but really what we want something is we want to get to our Michaelis-Menten equation. That's where we're headed, where what we do is we dump in a amount of substrate. We know how much we added, right? It's like what you did for your enzyme assays 2 weeks ago. What you did is you put in an amount of substrate. You knew how much it was. You could calculate how much substrate you had there. You put in how much substrate you have, and then you just vary how much substrate you're adding, which you did not do last time, but you will do. And then from that, you can figure out your Vmax and your initial rate. Okay? You'll get your initial rates, and then you'll figure out your Vmax from that, and you can figure out your Km then. Okay, so we need to get rid of this ES, right? Okay? Need to get rid of this ES. Unfortunately, getting rid of the ES is a bunch of algebra, but it is just algebra, all right? We made a simple model. We have an assumption that we have small amounts of enzyme compared to our substrate. And now we're just going to do algebra to it. We'll have another assumption, but we're just going to do algebra, make one more assumption, and we're going to come up with that Michaelis-Menten equation. Yes?
Where's the K2? Or is it just?
There's no K2.
Okay, that works.
I don't remember where K2 went. Maybe sometimes people will use K2 for this.
Mm-hmm.
And K3 is going to kind of become Kcat. The books separate them out because it's not exactly, you have to admit there's another assumption you make. But when we start bringing up Kcat, I have sometimes done this derivation and just expressed K3 as Kcat. Today my mood was such that I decided that since it wasn't exactly correct, I'd follow what's in the textbooks. So we have what's called now, we have one more assumption. We have the steady state assumption. All right, and what the steady state assumption says is that the breakdown of enzyme substrate is going to be equal to the formation of enzyme substrate at the beginning of the reaction. I'm going to call it enzyme substrate complex because it's a complex of two things. So the breakdown of enzyme substrate complex is equal to the formation of enzyme substrate complex at the beginning of the reaction. And that is this thing when I talk about initial rates. This is initial rate before 5% of your substrate's used. This is why I'm obsessed over these straight lines that you get in lab, right? It has to be straight, can't be curving, can't be, reaction can't be all done because that initial rate is really important. So let's see if we can keep our assumption or our model on screen here, and let's talk about what those two things are. So the rate of enzyme substrate formation. Right now I'm going to go to enzyme substrate formation, ESF, okay, is equal to what? What's my rate of making this with the arrows you have and the constants you have there? Exactly. So K1 times E, right? Because E is one of the substrates or one of the reactants times the concentration of S, like that. All right, that's my rate of formation. What is my rate of enzyme substrate breakdown equal to?
Like, will we get negative the KS times K3
Okay.
times ES?
Okay, so it's going to be K3 times ES. That's one breakdown direction, right? So let's add that. Plus, what's the other one? Yeah, we could fall apart and go back this way. All right, and what we're saying by this assumption is that these two things are equal. And so we can set them equal to each other. All right, so we're going to leave our other stuff behind. We don't need it now. At least for now, we'll need it. It'll come back. Whoops. So our formation is K1 times enzyme times substrate, and that's equal to K3 times enzyme substrate complex plus K minus 1 times enzyme substrate complex. Okay? We still have enzyme substrate complex in here, so it's still a messy thing and it's hard to measure these. So we want to get rid of all the E's. That's where we're headed. All right, so now we're going to start doing some algebra at this thing. You can imagine that what we've got here is I can divide both sides of this by enzyme substrate complex. And then what I'll get is I'll have K1 times enzyme times substrate, K3 enzyme, hold on. I divided it, so I get to cancel those, right? That's the whole point.
Wouldn't the left side also be divided by E?
Yes, thanks. So you guys can check my math as I go along here. Or check my algebra, I should say. Yes.
Can you explain the K minus 1? Like, why for the breakdown? Can you just kind of point it out?
Where is it in that model?
Like, yeah, like if you're going backwards.
So if we're going backwards, the rate constant for going backwards is K minus 1. So the rate for this reaction is K minus 1 times the concentration of the reactant, which is enzyme substrate when I'm going this way. Does that clear it up?
Yeah, but why is there 2 Ks for the backwards and only 1 K for the forward?
Because it's for the breakdown, you mean?
Yeah, for the breakdown there's 2.
There's 2, right. So this is breaking down the enzyme substrate complex, and this is breaking down the enzyme substrate complex. These are both ways, that's a great question. These are both ways that enzyme complex is going away.
Okay.
And maybe breakdown, maybe the term breakdown is confusing.
No, it makes sense, but I just figured if like you break down two ways, you form it.
Right, but we don't, with this model, we assume that this step is irreversible.
Okay, that makes sense. Okay, thank you.
Okay, so now we're here, okay? And what we can do now is I'm going to take this K1 and divide both sides by K1. Notice that I'm using little k's, okay? And I'm going to just right here rewrite this, and then we'll carry it on maybe. I'm going to define this big K, that's our Michaelis constant, is breakdown rate constants over formation rate constants. Now I don't know if you remember this from general chemistry, but if I have a reaction, let's say it's A plus B goes to C, and it's a reversible reaction like this, and so I have a Ka, let's call it a Kc and a Kab. Okay, I can write my equilibrium constant for this reaction is going to be products over reactants, right? Okay, but it also is, this is where thermodynamics and kinetics come together. It also can be that rate constant over that rate constant. Okay. You guys remember that? Maybe you don't. But that's what's going on here. Remember how I like to say that Km is like a dissociation constant, right? Dissociation constant is the reaction where you'd have two things breaking up. Actually, I should have written that. I could have done better over there in terms of my example. But it's where you have two things breaking up. This is two things breaking up over two things coming together, right? So it's like a dissociation constant. Because what we've done is we've just combined the rate constants there to make it work. Okay, so let me figure out where I was. That's where I was. Oh, yeah. Okay, so now we've got this great equation, right? Let's go ahead and rewrite it. We've got Km is equal to enzyme times substrate. That's free enzyme times enzyme substrate product, the complex, okay? I still have, okay, great, I've got this equation. I still have things that are hard to measure here. Free enzyme's hard to measure, right? And enzyme substrate is hard to measure. We're going to get rid of all of our enzymes in the end. But something that is not as hard to measure is enzyme total, right? I know how much enzyme I dumped in, maybe, right, if I measured it. And the concentration of enzyme total is going to be equal to the free enzyme plus what? It's either free or it's not free, in which case it's bound in the complex. Like that. All right, and so I can rearrange this, and I'm going to actually, I want to sub in for this. So I'm going to rearrange the equation and make it I'm going to subtract enzyme substrate from both sides. And then I'm going to end up with enzyme is equal to enzyme total minus enzyme substrate. I flipped a couple things around there. What I was doing was I was subtracting enzyme substrate from both sides. guys with me with that? Okay. All right, so now I have enzyme, and so I can go ahead and I can take this bit here and I can sub it in right there. And from that, I'm going to end up with Km is equal to, now, enzyme total minus enzyme substrate complex times substrate over enzyme, substrate complex. I can now multiply enzyme substrate complex times both sides. I'm going to get rid of the enzyme substrate complex on the bottom here. So it's a mess of algebra, but we're still headed towards getting the Michaelis-Menten equation that has no enzymes in it, right? So then this is going to cancel with this, and now I have Km is equal to enzyme substrate is equal to, I'm trying to remember if I think I want to split these up. So let me look at my notes. Yeah, that's a happier. I'm going to distribute the stuff on top. So I end up with enzyme total times, substrate concentration minus enzyme. Yes. Have I made a mistake here? Okay. Question? Nope. Okay. And now I'm going to add enzyme times enzyme substrate to both sides. And that's going to get all my enzyme substrate on the same side. Like that. And so now I've got the K. I keep doing, notice the Kms are big Ks, right? Not little Ks. It's essentially an equilibrium constant. Like that. And that's equal to enzyme total times substrate complex. We are almost there. All right. You guys with me? I'm going to divide by enzyme substrate complex on both sides. Okay, and that's going to cancel there. I didn't factor it out. Could have factored it out to make it more obvious. You see if I divide both these terms of enzyme substrate, you okay with that? All right. And now I have Km, whoops. I have Km times substrate, or no, Km plus substrate. It's not going to be as cool if I don't do it that way. Is equal to enzyme total times substrate over enzyme substrate. Let me see if we are finally at the point. Yep. And now I'm going to multiply my enzyme substrate over. Actually, I'm going to swap these two, but I'll do it in two steps. So I'm going to multiply this times enzyme substrate and this times enzyme substrate. Did we just do it? Did I do it twice? Yeah, I wanted to get rid of it. Yeah, I didn't need to do that. But anyway, we're going to stay here. So I did it and I undid it. It'll be okay. So now I'm back to where I have this. Okay, so we're here. If I now divide both sides by Km plus substrate, that's the big thing. Okay, and this cancels, leaving me with enzyme substrate complex is equal to enzyme total plus substrate, Km plus substrate. All right, we are almost there. Doesn't this look familiar? It looks kind of like, remember our Michaelis-Menten equation? Looks like V naught is equal to V max times substrate concentration over Km plus substrate concentration, right? So all I need to do is turn this ES into V naught and this ET into V max. All right, and so for that, we just need to, we're not making an assumption here. We just need to look at our kinetics again. Remember from our original model that we have enzyme plus substrate is going to go to make enzyme substrate complex is going to make enzyme plus product, right? And we've got our little K1 and K, these are little Ks, K minus 1, K3 here, and now K3 is going to become Kcat. The rate of our reaction is equal to V naught, we're going to say, and that we're just going to call that V naught, the initial rate, and that's equal to enzyme substrate complex times K3 that we're going to now call Kcat. So Kcat times enzyme substrate complex. Okay, that makes sense, right? Kcat is K3. There are special cases where they're not the same, but this is how books do it. And so I'm going to stick with that. So then, now what if, so Vmax is going to be equal to Kcat times, so we've got an enzyme substrate complex, right? Here's our model. What's this is does this vary? This is a constant, right? It's a rate constant, doesn't change. So the only way this reaction can go faster is for me to get more enzyme substrate complex, right? So we can do a Chateliers. I can add some more substrate, and that'll shift. I'll get more enzyme substrate complex. I can keep doing that, right? Where does it stop? Can I keep doing that forever? Get more and more enzyme substrate complex? They're all bound, right? Remember our assumption was you have much smaller amounts of enzyme than substrate. So eventually you bind all your enzyme to substrate, and it can't go any faster. So what that is that's the total enzyme you added. Remember, enzyme total is equal to, and this isn't an assumption, this is just, it has to be, right? Enzyme total has got to be equal to free enzyme plus enzyme substrate complex, right? There's no other place it could be. And so looking at that, so the absolute max that this could be is when this is 0, when enzyme total is equal to enzyme substrate, right? So V max is Kcat times enzyme total. And then let's look at this thing. If we come over here and we go and we put some Kcats in, right? Do you see now that what I can do is V max is this, and V naught is this. And if I put my V naught in, and I put my V max in, and then I leave everything else the same, I get the Michaelis-Menten equation. It's all just algebra.
Can you repeat the part about when the enzyme equals 0, that's the max enzyme substrate?
So you score in, that's a good question. So you scored in a certain amount of total enzyme. And that enzyme can either be bound to substrate or free. As I add more and more substrate, more of this enzyme, free enzyme ends up going into the enzyme substrate complex. And at some point, I've added so much substrate that it's all enzyme substrate complex, right? And that, so and then that's when it's going, the reaction is going as fast as it can. It can't go any faster than always having enzyme bound to substrate. Does that make sense?
And that's when E equals 0.
So E, when all of my enzyme is bound to substrate, enzyme substrate complex is equal to the total enzyme. Yes? Okay. So our maximum rate is when all our enzyme is bound, all our enzyme is bound to substrate. So all the enzyme we dumped in, our enzyme substrate complex is equal to the amount of enzyme we dumped in, or the concentration. Is that good? Bridget?
Where did KCAT come from over there?
We'll make it up.
Okay.
I mean, KCAT is K3 really.
So was it just like kind of there the whole time?
It was sort of there the whole time as K3, but there are conditions. There's an assumption here that so there are conditions related to how fast.
I mean, yeah, but like.
There are conditions where how the assumption here that makes this all work and makes Km be a Kd is this is slower than these. Okay, and so you get into trouble. K3 is not exactly KCAT if that assumption is not true. Okay, so like I said, I sometimes go through and I just don't say anything about K3, and maybe that's the right choice. I'll reconsider it for next year. But your book will have derived this and used K3 all throughout, and at this point it introduces KCAT. So a textbook doesn't really have the luxury of saying something that's incorrect and just telling you, yeah, this isn't right, but it's important for you later to learn it then. I don't know if that helps or not, but you could take K3 through this whole derivation, just make it KCAT. Effectively, unless you do something really specialized, it won't ever matter.
But like we got rid of K3 by replacing it with KM. So.
Yes, but okay, if that's the question, KCAT. But we know this is true, right?
Yeah.
So we're putting this is true. So we just brought it in, and now we have something that we can substitute.
So we're just adding it.
We're adding it. We're bringing it in.
Mm-hmm.
These are two true statements. They just have to be, right? Mm-hmm. And then if we multiply both sides by KCAT here, we can do that because it's algebra. Then we can sub in this V max and this V naught. Yes.
So we did all that so that we can have values of our enzymes into the Michaelis-Menten.
So we did all of that so we could get this equation. And that allows us to determine things like Km. We'll also be able to determine KCAT. Okay, because we can determine Vmax. If we can determine what Vmax is, we can figure out what KCAT is from it because we have this equation, right? We know how much enzyme we dumped in, and if we figure out the Vmax, then we can figure out the KCAT. So those are the two things we want to get from that, right? So KCAT, let's talk about that. That leads into a good question. KCAT, actually let me type this. KCAT is called the turnover number. Okay, it's the maximum number of substrates of substrates an enzyme can convert to product in a given amount of time. Actually, let's say the maximum number of products an enzyme can produce in a given amount of time. All right, so this goes for if you have a single enzyme, you can think about this from the single enzyme perspective, okay? For example, a kcat of, let's say 567 per second, and that would be our units on it. So seconds to the -1, okay, means a single enzyme molecule, right, they're big molecules, can make 567 products per second when it's saturated. In other words, when we have so much substrate around that the enzyme is always bound to substrate. Does that make sense? What kcat is? What it means? Okay. And it's a lowercase k. Okay, Km. Km is essentially a dissociation constant. Okay. The lower the number, the stronger the enzyme binds the substrate. Or let's say the more tightly. Questions on those two? They are super important. Okay. Questions on other stuff we covered so far? Let's remind ourselves of what we can do with this equation. So once again, V naught is equal to V max times substrate concentration over Km plus substrate concentration. As we talked about last week, we can divide both sides of this divide 1 by both sides of this. And then we end up with an equation that gives us a line. So essentially 1 over V max is going to be Km over V max times substrate concentration. I'm sorry, 1 over substrate concentration plus 1 over V max. Okay, so if we look at this from last week, right, so what we do is we take this and we're going to divide 1 into each of these. And so we can flip this, right? And before we do that, we can separate these two out before we flip them. So, right, because we have the same denominator here. And then we flip this one and end up with Hold on, I've already flipped it. Sorry, I'm confused. All right, so we flip it, right? And that's just straight out what it looks like. We can separate those out and then get this. All right, and that's useful because it's a y is equal to mx plus b equation, and we can like then start pulling out we can vary. So if I plot 1 over my substrate concentration over versus 1 over my initial rate, I'm going to get a straight line. The slope of that straight line is this. The intercept, the y-intercept is that. Okay, so very useful in terms of doing this, in terms of plotting. Questions? Yes.
At the end of last class, you said that 1 over Vmax can be used to find the constant. Do you take the slope and the intercept then to find that? Is that what it means, or?
So 1 over Vmax is this intercept.
Mm-hmm.
And once I do that, I can solve for Vmax.
Mm-hmm.
And then I can put Vmax over here into the slope and solve for Km.
Okay.
I don't know whether I'll do it today, but you can also solve for Km is actually 1 over negative 1 over the x-intercept. I'll do the math for these. Not today, I don't think, for that. Okay. But it's actually a faster way of getting it. Okay. So we have that. That's useful. But before I go on, I should talk about graphy things. All right, I'm going to use these graphy things to test your understanding of this equation and the derivation. So let's try a few. All right, so let's go ahead. We're going to I'm going to put the Michaelis-Menten equation here. It's not going to be good for all of graphy things because some of the things were assumptions we made along the way. But let's go ahead and put up some of the various equations that we needed. So we'd use this, right? We talked about Vmax, and that was equal to Kcat times enzyme substrate concentration, right? We had V naught was equal to Kcat times enzyme substrate concentration. Actually, sorry, Vmax was times enzyme total. I'll just leave it as a T like that. Okay, we've got that. And then we also have our steady state equation, right? That says our enzyme substrate complex is not going to change over time. But let's just start with a basic one. If I take this, I vary my substrate. What happens to my initial rate as I vary substrate? Think about how the top equation changes as substrate is increased, particularly how substrate relates to Km.
Start out with more substrate.
As you add more substrate, it's going to get faster, yeah? And then it levels off, right? So you can think about this. You could also think about the model for this, right? Eventually add so much substrate the enzyme can't go any faster. Okay, so you could think about it using this equation. You could also think about it using this model. Right? If I keep dumping in substrate, eventually, because enzyme is much smaller than substrate concentration, I'm going to saturate the enzyme, and I'm not going to be able to make any more substrate. So we get this. Okay. What about Kcat versus enzyme concentration? What would it be? Louder?
Like indirectly related? It's on the same side of the equation.
Are they indirectly related?
Or like, cause like they're on either side of the equal.
What is k cat?
It's a constant.
It's a constant. So it's a trick question, but I say usually I won't ask you trick questions, but this is an exception.
You asked
Okay.
a trick question the only thing.
Did I? Okay. Okay. So that's one of those things. What if I asked you, what if we looked at, we took I could say at the beginning of the equation, at the beginning of the reaction, okay? Or I could say for an initial rate, what's my enzyme substrate complex concentration going to be versus time? Where it's just at the beginning of the reaction. Is it going to be a diagonal? What does our steady state equation say?
Over time, when it will be balanced.
It says that enzyme substrate complex isn't changing, right? The rate of formation is equal to the formation rate of breakdown at the beginning of the reaction. So there's going to be a straight line, or you could argue that, well, it has to start and then become a straight line. So I'd take either of those. So that, or if you just did this, both of those are fine. So, but these are things we're thinking about what's going on with the reaction, right? What about, well, let's actually do V naught. What about V naught, how fast the reaction goes with enzyme total concentration? You have some experience from this from 2 weeks ago.
Straight line increase.
Like it depends. Except when we did the
Right? As you add more enzyme, at least over some levels, as you add more enzyme, the reaction goes faster. If you add twice as much enzyme, the reaction goes twice as fast. This assumes that your enzyme's limiting throughout that range, which it is. This is what your dilutions were about, right? You did a straight dilution. You did a 1 to 10 dilution, then you're going to multiply it times 10 to get what that original concentration was effectively. You see what sorts of things I'm going to ask here? These are the sorts of things. I might ask these. I might not. You go back. They're practice tests, right? There are two years of previous tests. At least one of them will have some of these on them. Yeah, Claudia.
Oh, can we talk a little bit more about the enzyme substrate concentration over time?
Uh-huh.
So we were just talking about how like enzyme substrate is equal to like 0. So why over time is there not more enzyme substrate?
So let's. That's a good question. Let's go ahead and let me clarify that. So we talked about how we started saying that enzyme total was equal to enzyme substrate concentration plus it's the free enzyme and it's bound enzyme. And that's the only two places it can go. And then we rearranged this because we wanted to, I don't know that we actually rearranged this for what we're talking about. So what we said is when the enzyme is going as fast as it possibly can, that our enzyme substrate, that this is 0, that we have our equilibrium here where we have our enzyme plus our substrate goes to make enzyme substrate complex, and then that enzyme complex, the enzyme can make product and release it. Okay, so this is going as fast as it can. We've added enough substrate that this is all the enzyme is saturated. There's no free enzyme. Okay, so every time that product gets made instantaneously, which isn't almost instantaneously, right? But instantaneously, a new substrate pops in. Okay, So that is a special case. It still works for this, but that's a special case. That's not necessarily what's going on in this graph. Because this graph, we don't necessarily have this be equal to ET. This is only equal to ET when we've added so much substrate that all of it's pushed over this far. Is that helping? Doesn't look like it's helping.
So the blue lines would lose that.
So let's do this in the case where we're at Vmax, right? This isn't Vmax. Vmax is where all the enzyme substrate is in that. At Vmax, it'd be the same graph, it'd just do that. It'd be higher.
So it's not like we're adding more enzyme.
You don't add more enzyme when we're at Vmax. Let's take a look at a graph here. So if I want to look at my initial rate versus substrate concentration, I get a graph that looks like this. I'm adding more and more substrate as I go, and where this would go at infinity, right? Where it looks like it levels off, but it's really where it's going to, if it was still going up. That's my maximum rate that I can get for the amount of enzyme I added. Because all that enzyme, when I add essentially this much substrate, whatever that is, in terms of the concentration, all the enzyme is trapped in enzyme substrate complex. And this little run-up thing I'm doing here is just that, when you squirt your enzyme in, you in the very first instant don't have enzyme substrate complex. But certainly in terms of what you measure, in terms of the amount of time it takes to mix it and get it to a cuvette, it's all enzyme substrate complex, and it's steady state at that point. And if you've added a ton of substrate, it's actually all enzyme substrate complex and there's no free enzyme. Does that make sense? Yeah, we can talk more about that later. Other questions on this? Okay, so I want you to look at that worksheet there. We don't have time to do much of it, but let's just go ahead and look at that and start thinking about it. I want you to give that a shot. So what that is, that worksheet involves trying to actually solve one of these things. And so for your next exam, you won't have to do this on paper, on a worksheet, like a graph on paper, but for your final exam, you will. All right, because we have lots of time for a final exam. And so you've got a set of data there. There were a few extras, were there? So I can look what the data is. We're trying to do a Lineweaver-Burke plot, right? That's where we took those things and put them upside down. This is all extra drafted. So I've got this initial data that I've got how much of a substrate I've added, right? ADP. And we've got our reaction up above, and that's micromolar. Then I've got 20, 40, 70, 150, 300. And then I've got my initial velocity in millimolar per second. And that's going to be 10.83, 18.57, 26.76, 39.00, and 48.75. Okay? What is the first thing I need to do? I'm going to try and generate a Lineweaver-Burke plot that looks like this. What's the very first thing I need to do here?
Convert.
I need to convert. I need to, more specifically, well, I don't have, that's a good question. Do I have to make these equal? And I'm going to tell you I don't, actually, Ann, which is actually another great thing about these. You don't have to actually match these. But I want to plot 1 over substrate, right? And I want to plot 1 over velocity. So the first thing I have to do is I need to divide 1 by all of these things. So 2 new columns, and do that. We don't have time to do that right now, okay? But what I want you to do is, I guess I don't want you to try that before Wednesday, but I want you to bring those worksheets back. Don't lose them. okay? And we will work through that thing on Wednesday.